invitation. I'm very pleased to contribute to this Italian-French meeting on heritage science. And I would also like Michel for his inspiring introduction, which set the stage for showing the evolution of the concept of heritage object. In my talk, I will show how the conceptual framework presented earlier can be made operational through an IoT sensor network and dynamic digital twins. I will also introduce SENNSE, the platform we developed at CNR ISPC, to integrate real-time environmental data with structured knowledge, enabling predictive and proactive approaches to preventive conservation. So when we describe a cultural asset, we usually rely on three well-established categories of knowledge. The first one is the historical and artistic information, which includes its origin, transformation, and intangible cultural value. The second one is relating to its physical structure, layers, techniques, and components. And the third one is its let's say, aesthetic and structural qualities such as shape, geometry, and visual appearance. These three dimensions are essential to understand what the object is. However, none of them can tell us how the object is behaving right now. For preventive conservation, we must consider a fourth category: real-time conservation status information. This includes the environmental and microclimatic conditions that the object experiences continuously: temperature, humidity, light exposure, surface wetting, and all the dynamic factors that affect its stability over time. This fourth dimension is fundamentally different from the others. It is fast, variable, and event-based. It transforms our understanding from a static description of the object to a dynamic awareness of its ongoing conservation state. Once we understand the digital twin as the full body of knowledge associated with a cultural asset, the next question becomes: how do we represent this knowledge? Different data models have been developed over time, each one capturing different facets of the object and its history. Most traditional approach, at least to me that I'm a software engineer, was the relational model, which organizes information into tables. It is essential for well-structured dataset, but it struggles when we need to represent, for example, complex relationship, events, or evolving state. More recently, the semantic model has gained importance. Using ontology and knowledge graph, it allows us to express not only data, but also the meaning of the data, the relationship between materials, diagnostic analysis, environmental conditions, and past events. In fact, at the European level, this perspective is fully aligned with the European Collaborative Cloud for Cultural Heritage, in which is built on a knowledge graph approach to semantically integrate documentation, diagnostic, and monitoring data across the institutions. As we look at different types of information that contribute to digital twin, it becomes clear that they do not behave all in the same way. A large part of heritage knowledge consists of what we can call slow data. Let's say slow data. Geometry of the object, historical documentation, archival sources, diagnostic analysis. This data change rarely, sometimes only once in decades. On the other side, the modern IoT infrastructure generates what we can describe as fast data. These are high-frequency environmental measurements produced by continuously in large quantities, and they are true big data streams characterized by what we usually call as the 3 V's: data volume, data velocity, and data variety. Because low and fast data are so different in nature, they also require different approaches to storage, processing, and integration. For IoT streams, we need databases and architecture specifically designed for high throughput ingestion, real-time analysis. This is why within SENNSE we adopt an IoT-ready hybrid data infrastructure capable of supporting the real-time behavior of the digital twin. To better understand the role of SENNSE, it is useful to see how the platform generates three complementary, let's say, images of the monitored heritage asset. The first one is something we can call static image. Let's say the slow, something like a slow image based on the knowledge graph. Knowledge graph allows us to represent the object, the site, the building through its materials, its historical transformation, its diagnostic investigation, and all the contextual information that define its identity over time. The second image is dynamic representation of the monitoring process itself. This includes the selection of measurement points, the choice of the physical parameters to be acquired, the full configuration of each sensor node, going from sampling frequency to operational modes, calibration session, and all the activities that define the workflow. Tracking these steps is crucial because the process that generates data is part of the knowledge itself. And the third image is the real-time trace produced by the sensor networks. SENNSE records, aggregates, and stores real-time series data, enabling continuous observation on how environmental conditions evolve around the asset. Now that we have seen the conceptual foundation behind SENNSE, let me briefly introduce the platform itself. SENNSE is an open, extensible environment designed to support the full cycle of environmental monitoring for cultural heritage. It has been developed within the Institute of Heritage Science for the IRIS research infrastructure under the PNRR-funded project H2IOSC. Its goal is to provide an unified digital space where data capture, analysis, visualization, and interpretation converge. SENNSE integrates wired and wireless sensor network, time series databases, semantic knowledge structures, and enables machine learning modules for predictive analysis. It also includes advanced visualization interfaces that we will see in the next few slides, dashboard, 2D analysis tools, and immersive 3D navigation that help us to connect measurement with the physical and historical dimension of the asset. From a more technical point of view, our position is that no single data model is enough to support a dynamic digital twin. Cultural heritage monitoring operates on different temporal scale, different data behavior, and different degrees of semantic complexity. For this reason, SENNSE adopts an hybrid architectural approach. At the first level, we use a relational database based on PostgreSQL. These manage all the configuration aspects of the application, project definition, sensor metadata, workflow description, and also the monitoring parameters. At the second level, we rely on an hyper-timed series database built on TimescaleDB. This component handles the high-frequency environmental events and large volumes of time series data generated by the wireless and wired sensor nodes. And finally, the third level is the ontological one, implemented through BlazeGraph and integrated into Digilab, I mean the Italian node, obviously, of Digilab, the semantic platform that manages the scientific cultural data lifecycle as tribal store. This semantic layer allows us to link measurement and events to the broader knowledge ecosystem of material, diagnostic analysis, historical documentation, and conceptual entities that define the heritage asset itself. To illustrate how SENNSE operates in practice, I will present a case study, the Grotta degli Animali, located in the Boboli Garden in Florence. Originally conceived by Tribolo and later redesigned by Giorgio Vasari and Gian Bologna, the grotto is a remarkable example of Medician garden. Combining stone sculpture, hydraulic mechanism, and complex, that you are seeing now, and complex decorative surfaces. This is an environment with both artistic and technological significance, an intricate interplay of material, of water gains, of porous stone and decorated surfaces, but its aesthetic qualities depend on extremely delicate microclimatic conditions, which makes it an ideal case for deploying a dynamic and predictive digital twin. The Grotta degli Animali is a highly dynamic and fragile environment. Humidity and temperature fluctuate significantly across seasons, and the activation of the water system generates obviously environmental changes that can stress materials. To capture this complexity, we deployed a sensor network composed of wired nodes. These sensors nodes monitor, for example, temperature, relative humidity, and many other parameters. Additional sensors detect surface wetness, water levels, providing a more granular understanding of the condition affecting different parts of the grotto. All these measurements are ingested in real time by SENNSE continuously from last February, stored as time series. In a cultural heritage monitoring project, it is not enough to collect only environmental data. It is essential to keep track of the entire monitoring process and to document it in a structured and meaningful way. This means, first of all, establishing a clear semantic connection between each acquired measurement and the specific cultural asset to which it refers. We need to know, so, not only what we measured, but also where and how and under which conditions. For this reason, SENNSE allows us to precisely define the measurement points under observation, to specify the physical parameters associated with each of them, and to record the full configuration of the related sensor nodes. In this project, the sensor nodes used in the Grotta degli Animali were fully designed and engineered in our laboratory to meet the specific environmental constraint of the site. Each of the three basins were equipped with sensors capturing the local microclimatic dynamics, and all the nodes were installed through a wired Power over Ethernet architecture. The design and the configuration of the nodes also have been formally documented and published in the IEEE SoftCon conference, where we described both the hardware architecture and the methodological choices behind this monitoring setup. These photos show the installation of inside the Grotta degli Animali. A key aspect of the project was designing a non-invasive cabling system fully compatible with the conservation constraint of the site. And all the wiring was routed through the rear service corridor, allowing us to reach each of the basin without interfering with the surfaces decorated. Also, the same corridor have been identified as critical microenvironment because their high humidity and early microfractures in the masonry. For this reason, we have planned a second monitoring campaign aimed to deploy additional sensor directly in the corridor to track their microclimatic behavior and assess potential risk. SENNSE also provide obviously several user interfaces types. On the left, there is the time series viewer. On the right, a more intuitive 2D view displays the current microclimatic values directly on the grotto layout. Maybe more interesting is this slide in which we can see how SENNSE project environmental data directly onto 3D digital twin of the Grotta degli Animali. This special representation allows us to link each measurement to its precise architectural and material context, revealing which areas of the grotto are most exposed to the microclimatic stress. The platform also supports immersive navigation, which is particularly useful for exploring complex spaces or for remote inspection. And we are at the end. Up to this point, we have seen how digital twin typically integrates historical, material, and geometry information with the environmental data collected close to the object, such as temperature, humidity, light condition, and monitoring in the monitoring area. This means that the predictive capabilities of the twin are inherently limited to what the system knows about its immediate context. But we can imagine a different scenario. What would it happen if the decision-making system had access to a much broader contextual depth? For example, weather alert system, public safety information, satellite-based remote sensing, or civil protection data in real time. If these external layers of context were connected to the digital twin, we would move from local prediction to multi-scale anticipation of risk, not only environmental, but also structural, climatic, or even anthropic. This expanded contextual depth would radically transform our ability to forecast, prepare, and react, opening a completely new horizon for the protection and long-term resilience of the cultural heritage. I would conclude by thanking of the colleagues of the DHI lab who contributed in different way to the results I presented today, and also to the researcher group that studied and participated to the ongoing environmental monitoring project of the Grotta degli Animali. And finally, my closing words are for Vincent et al., whose legacy continues to guide our shared work. Thank you all for your attention.